Welcome back, everybody. So before we continue, I will ask you 3 questions on the Clicker app, and then I will show you the JSONic sandbox, right? So let me first ask you questions. This should be quick because I told you, right? This is just checking that you are following. So, which of the following adjectives qualify a well-designed query language? Functional, imperative, low-level, declarative. That should almost be an automatic answer. All right. So let's look. Functional and declarative. Yes, these are the main 2. Imperative, no. This is what I said earlier, that it's harder to, well, let me not tell you why, because I have a question on why, right? So functional, declarative, the 2 words. Now I can ask you, why? Why should a query language be functional and declarative? So that queries can be parallelized, so that an optimizer can make the query faster in order to delegate the details of the execution, or because queries are more concise and easier to read and understand. Aha. You don't like the first one? Okay, here's the solution. Everything is correct. All of these are reasons why a query language should be functional and declarative. We can parallelize, we actually do on Spark. An optimizer can make the queries faster. You can delegate the details of the execution, and queries are also easier to read. Right? These are all valid reasons. And finally, what does the JSONic data model, JDM, process? That should take you just 2 seconds to answer this one. Yes, 100%. Wow, you are awesome. Yes, 100%. Sequences of items, indeed. All right, and now the other thing I wanted to show you is that if you go to jasonic.org, so that's the website of JSONic, there is this little link here, live tutorial, which you can open and follow. It's going to open a Jupyter notebook. It works if you have a Google account. If you don't have, it's okay if you don't have one, then you can just run it locally in your laptop, right? Just like we do with the exercises. You have these 3 lines that install the Jupyter connector. You just need to confirm here. And you see here, this is a backend of RumbleDB, public.rumbledb.org. It's a public backend. It's actually a super tiny machine with just 1 GB of memory and 1 core, but several of them. That's just meant for playing. So anybody who wants to play with JSONic on that backend can do it. In that case, you just leave it unchanged. But of course, if you prefer to play with your own installation of RumbleDB, as we'll do in the exercises, then that works too. So once you have done that, then you can just go ahead and click on these queries, and this automatically is executed by the backend. And of course, there's the whole tutorial. So here you see that, so these are the very simple queries. You just need to click to execute. And then if you go to the end, that's what we are about to do now. At the very end, you have examples of relational query, like where join, and so on and so on, right? So I'm not going to execute that right now, but this is where to go if you want to dive more into what we've been doing. All right, let me go back now to the slides. Somehow where everything is just not working, and that happens, and we just have to deal with it. All right, so welcome back. So let's talk about flower expressions that look like that. So for lets where order by return. Let's start with the let clause. The let clause is the easiest. So the let clause allows you to bind the variable. It's not an assignment, right? It's not that you modify the value of the variable. It just says, okay, x is 2, you bind it to 2. And then you return x times x, which is 4, right? So this particular expression returns 4. Here's another one now with the for clause. So the for clause binds a variable to multiple values in turn. What this for clause here does is that it binds $x with 1, and then with 2, and then with 3, and then with 4, but one by one. Right? So $x is always associated with one value at a time. And for each one of these values that it can be bound with, we calculate what's in the return clause, which is this number square object, right? And it's like a map. So every one of the values from 1 to 10 is going to give you one object. Right, so there's number 1 square 1, number 2 square 4, and so on and so on. Do we have a question in the chat on Zoom? Okay, it's from earlier. All right. So far, so good. Is it clear, the for clause? All right, here's the next one. It's a where clause.
There's a question in the chat now. But did we not say that the execution is done in parallel?
It can absolutely be done in parallel. Imagine, how can we do it in parallel here? We could execute it on 5 machines. One machine takes care of 1 and 2. One machine takes care of 3 and 4. Another one from 5 and 6. The other one 7 and 8. And the last machine 9 and 10. That can absolutely work in parallel, just like in Spark, right? So that could actually be implemented in Spark with a map, right? That works with a map in Spark. So you can map, you can build an RDD with 1 to 10. Then you can have a map transformation that maps each number to an object, and that's it. So it does work in parallel, absolutely. But of course, at the end, once it's done in parallel, you get all of the results, right? You collect the results and you get that, right? Does it answer your question?
Got it. Is it per default in parallel?
That depends on your implementation. With RumbleDB, it's not going per default in parallel. If you want to make it in parallel, you just need to add a parallelize around the 1 to 10. In the future, it's likely that we will have a threshold. Like, for example, if you have more than 1,000, then it's automatically going to do it in parallel. But this is an excellent point. So in the present state, just add parallelize around 1 to 10. That's gonna do it. But you're absolutely correct that the spirit of data independence is that normally you shouldn't have to do it. Normally the engine should figure it out all by itself. All right. So now the where clause. What does it do? Well, it's like a Spark filter, in fact. So you have this $x that is bound in turn to 1 to 10. But of course, you can also do it in parallel. There's no problem with that. And then you filter out all of these values of x for which this condition doesn't hold. And you only keep those for which it holds. So in that case, we just keep 8, 9, and 10. And then we get the squares of 8, of 9, and of 9, and of 10. Right? Is it clear? Everybody? All right. So this is the where clause. And again, you see the where clause can also be done in parallel, right? You can have a Spark filter in parallel. All right. Next, we have the order by clause. So imagine I have a list of all countries in the world, and I read them in parallel. That can be on a cluster. Even though, of course, as you can imagine, with just a few hundred values, maybe it's too much to use a cluster for that, but it's just for pedagogical purposes, right? All right. So for $x in the list of countries. Imagine I want to order them by population descending. So this is the descending list by population of the countries in the world, and I return their names, right? So this is order by, that's the O in flower. It's very similar to the order by in SQL, right? You can have desk, ask. So here it's just descending, ascending, and so on. And group by, it's also similar to the SQL group by, where you can say, okay, for $X in the countries, group by continents. Now I'm grouping by continents. So I have Asia, America, Europe, Africa, and so on. And now $continent is going to hold one continent at a time, obtained from $x.continent. What's interesting with the group by, it's what's happening to $X. Because what's happening to $X is that before the group by, it had one value at a time. After the group by, $X has the sequence of all the values that are in the same group, right? This is what happens. So once you have done that, you have the code with the continent. Interesting. You have the code of the continent, and then in the countries, you see that something you could not do in SQL. You can have this $X here, that is the sequence of countries within my continent, and you can add a nested for loop for each country in $X within my continent, return the name of the country. And this is what you get, basically, right? If you do it. Does it make sense? Yes? To you too? Yeah. Yes?
There's a question. Can you repeat, please?
Yes, absolutely. So here what's going on. You have to look at it top down, right? To start at the beginning of the for clause. So if you concentrate on for group by return, somebody, you might need to mute. Yeah, awesome. So if you start at the beginning of the for clause, so of course it's nested within this object, continents, blah, 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 but this is just a detail, right? So focus on the for group by return. For $X is going to bind X to each one of the possible objects in countries.json, right? Possibly in parallel. Group by continent is going to shuffle everything around and then create a group for each unique value of $x.continent. So there's going to be 6, right? Depending on your counting, if you consider North America, South America, the same or not, right? But it's the idea, right? 6 groups. So $continent, 6 possible values. But after the group by, what's going on is that this $X now, for each continent, for each group, is a sequence of the country's objects in the current group, right? So $X is a sequence after the group by. So that means that for every group, you're going to return an object with the keys code and countries. Code contains the continent. What's interesting is that if you look inside countries, inside this array, it's a mini iteration within my group. So $X has the countries within the continent that I'm looking at, and it's iterating on these and extracting .name, right? Okay, now you could observe, you could just have written $x.name, right? And that would have worked, yes. But I just wanted to make the point that you can nest the for in there, right? And this is what it returns, right? Was it better understandable?
Yes.
Yes, awesome. Okay. So now let me dive even more, because that was the intuition. But now let me explain the semantics, how it's actually defined in the specification, what's going on. It's called tuple stream. So for most users, they will not need to worry about that. This is something intuitive. But if you want to understand mathematically what these clauses do, this is how it works. Every time you have a clause that generates assignments or bindings, like here on the right, so the X, $X, is bound in turn to the value to 1 to 10, and you can actually view that almost as a relational table, this tuple stream. When you have the where, it's gonna, create a predicate on each one of them and only keep 8, 9, and 10, and then the return clause is gonna map it back to a sequence of items, because the flower expression has to return sequences of items, right? All right, is that clear? Okay, so that's the tuple streams for where return, and that's it. Now, here's what happens with the let. So I again start with the tuple stream. After my for clause, I have X with 1, 2, 3, 4, 5. $I, what does the let do? The let actually adds an extra assignment in the tuple stream. So it's like a new column in my relational table. And then X times I, why I just go on each tuple, each possible tuple, and compute x times y, and that gives me the result of my expression. Does that make sense too? Right. Here's another one, the group by. So again, here I create my tuple stream with the for clause, and I always go top down. So each clause by clause, group by is gonna compute the value of my grouping key for each one of them. So here modulo 2 is 1 or 0. And this is what's going to happen after the group by. So this is what I explained earlier, that once you have your groups, the key x that used to be associated with one value at a time, now it's associated with sequences, but for each possible group. This is what the group by does. Right? And then you have the return. And as you can see, foo is $y, and then we take the count of x. So this is something we could do in SQL, the count of x, and that's it. So this is what is returned. What is very important is that, of course, you see relational tables there. So you could think, okay, maybe JSONic manipulates relational tables. Yes and no. This here, what I'm showing here, these tuple streams and relational tables, is really a hidden physical detail of the way that the flower expression is executed. It's for pedagogical reasons, basically, that I'm showing you that. It actually turns out that RumbleDB implements this on Spark exactly using these sort of tables as data frames. So what you see here, it's actually going to be data frames that are going to be manipulated by Spark. Right. So if you want to understand what's going on. All right. How do we use? There's a question.
Yes. How do we use more than one keys in the group by?
I think you can with just a comma, like group by $y equals blah blah blah, comma $z equals blah blah blah, comma $t equals blah blah blah. So you can have multiple keys. Does it make sense? Just like SQL, in fact.
Yes.
Very similar.
Yes.
Okay. The one thing that SQL cannot do is, sorry, if I go back, this is the one thing SQL can't do. After a group by in SQL, you have to aggregate the order values, count, sum, mean, max, and so on. You cannot use in SQL a non-aggregated value, but in JSONic you can. That's the magic of a language that's just more generic than SQL. Okay, now a few words about types, because just like Python actually introduced type declarations very recently, JSONic has the same things. You can declare types. So the way it works, because we manipulate sequences, so I don't only need to say what the items are, integer, Boolean, array, object. I also need to talk about the cardinality of the sequence. Right? Is it one item? Is it 0 or 1 item? That's the question mark. Is it 1 or more item, array plus, that would forbid the empty sequence? Or is it any number? The star is for any number of items, right? This question mark plus and star, for computer scientists, it's very intuitive because they have something called regular expressions where they use the question mark, the plus, and the star to mean exactly that, right? So question mark is 0 or 1, plus is 1 or more, and star is 0 or more. And then you can have what is called sequence types. And then you can annotate, just like in the last version of Python, let $x as array plus, and it's going to throw an error if that doesn't match. So here it works, right? It's a sequence of 2 arrays, so that works. You can test, just like in Java, is it an instance of integer star? Obviously, that's going to say no. That's going to say false, because foo is not an integer. 3.14, castable as double. You can test for whether or not it can be cast as a double. So here, obviously, yes, you can cast that as a double number. And when you have functions, because yes, you can also have functions, you can define the type of each parameter like that and the return value. So here it's a function that takes an integer, a sequence of objects, and returns a Boolean. What's very important is that you can do that, but you don't have to. It's also fine if you don't put any types in there. It's also fine if you just say declare function, $threshold, $objects, and that's it. So you have absolutely no obligation to declare your types. But if you do, it helps the engine to optimize a bit more. All right. So now let me show you, it's probably obvious by now, but still pedagogically, I want to show you that. Let's do a bit of relational algebra. Let me assume I have 2 data sets. one data set called products.json that contains a few products, right? It's a JSON, one per line, and it's on S3 or HDFS, right? So you see I have the ID of my product, I have the type of product, and maybe the ID of the store where the product is being sold. And then I have a list of stores in the other data sets, right? With the ID of the store that corresponds to the store field on the left and the country. So let's do a few queries in there. Selection, as you know, in SQL is with the where clause, right? Exactly the same in JSONic. Selection is with the where clause. So here we select all the products where the store is one, and we get that. All right? That's selection. Projection, there is this project function. So here with the for loop, it's like the select from where, right? So the from is the for. For every product, we project $P to ID and type. So the second parameter of project is a sequence of strings, which are all the keys that you want to keep, right? In SQL, it would be select ID, type in products.json, right? That's basically what it would mean in SQL. Why is it more complicated than SQL? Why do we have this project thing? Well, because in SQL, you know exactly the name of your columns in SQL. You know them in advance, but not in JSONic. The data can be a huge mess. You might have like 1,000 different keys with an enormous mess, and you just want to say, I want ID and type and so on. So this is why the syntax is a bit more generic. Ordering is with order by, so we can order the IDs of the products. You see it's nicely sorted now, 1, 2, 3, 4, 5, 6, 7. You can group the products by type and count, types $T, that's the group, and $P would be the products in the group. But here I take the count and I get that. All right. So you see everything SQL does, JSONic can do. Here's a join. How do I do a join? Well, I can have a double for. I iterate on products and I iterate on store, and then I filter to make sure that the store matches, the store of the product matches the ID of the store. Right. And then I have in my output, by the way, that's also a way of projecting that I have type $P type and country $S country, right? And this is what I get. This here is optimized, meaning that RumbleDB will recognize that this is a join, and it is actually going to execute that as a join on Spark. So you can do that with, let's say, 1 billion products and 1,000 stores, and RumbleDB will efficiently execute that. Okay, you can also do, so here I'm getting a bit more technical, but basically you can also do what's called the left outer join. It's something that sounds complicated, but it's not that complicated. It's just the idea of what happens if we don't have any matching store. Imagine I have a store ID somewhere and I don't have any store. That's okay, because if I add this allowing empty, then that's still going to keep it in the output, right? So that's called the left outer join. Okay. Denormalizations, well, technically that's not part of the relational algebra, but I wanted to show that to you. Imagine that you have these two data sets and you want to merge them into the same data set, which would also, of course, be denormalized then. So what you want to do is nest the products within the stores. So what you do is that you iterate on the stores, then you iterate on the products, but of course filtering to make sure to take the products for that store. And then you return the country and products as a nested array. That's what you cannot do with standard SQL. And inside the products, you get all of your product types. This is called the denormalization. We take the two data sets and produce a new data set where now it's nested and denormalized. Does it make sense? Right? And then you can use that data set to continue processing your data, because then the join is done. You don't need to care about the join anymore. Okay, this is very challenging to do with SQL. Borderline impossible. You might be able to do it with maybe Spark SQL in a way, but this can be cumbersome. All right, let's go into the details of the implementation now. How does RumbleDB implement that? Well, since you actually asked, or people on Zoom asked about parallelism, I kind of already told you a bit how RumbleDB implements it, right? I already gave you a few details. So here's what's happening with RumbleDB behind the scenes. What's going on is that you have your query that's on the left, count for I, blah, blah, blah. That's a query that the user typed in Jupyter Notebooks. What RumbleDB does is that it's going to parse this query and convert it into this ugly thing on the right that's called an abstract syntax tree. It's just the way that the computer sees the program, which is just a structure that has the representation of the query. Right? So this is what it does. Of course, it doesn't show you, but it does that actually behind the scenes. Then what it does is it's going to further process this abstract syntax tree and convert it into that's actually a compiled version of your program that's called an expression tree. So it's basically like a plan of what to execute and how the expressions nest internally. So that's an expression tree. So that's what it's supposed to evaluate to return the results to you. And then you can do optimizations because the engine can then iterate on trying to find ways to make your query faster. It means that even if you got it wrong or didn't see that you didn't write the query well, a query engine is able to find out low-hanging fruits and optimize and rewrite a bit your query. So this is just an iteration. Spark does that as well, by the way. If you write Spark SQL and you didn't write your SQL query well, Spark is able to correct a few obvious things that can make it faster. And once it's done, it's going to take the expression tree and turn it into an iterator tree. Now, the iterator tree is actual computer code that is imperative. This is actually now Java, so this is imperative. And this is just going to iterate on the data or execute it in parallel and so on. So the execution then is going to happen like that, where you can see that there are sequences of items between the expressions and between the clauses. The clauses are not expression, be careful, for clause, let clause. It manipulates streams of tuples. So in this tree, you have streams of tuples and sequences of items. Now, what's going on is that RumbleDB, because it's a functional and declarative language, RumbleDB can decide how to execute. It has several options, right? So I'm going to give you the options. The first option that an engine can do, imagine that I have a for followed by a return. So I have my stream of tuples, right? So I have here 5 tuples that associate $i with a value. Materialized execution means that I take all of the items there and I literally copy them in the memory of my machine. I materialize, this is called materialization, right? So I really built the actual list of my tuples in memory on my machine, everything in memory, and then I execute the semantics of my iterator, and then I give the output. That's called materialization. The problem of materialization is that it takes tons of memory because you have to have the entire data, the entire output of the previous expression, a full copy of that in memory. So that's not good. In many cases, it's something that you can actually avoid and that you should avoid. And in order to avoid that, that's called streamed execution. So streaming means that instead of making a full copy of the entire input, you take them one by one. $i, field 1, okay, then you return the results. Then you take the next one, then you return the results. So you can see that this also works if there is much more data than the size of the memory. You could have 1 gigabyte of memory and 1 petabyte of data in there. You can still sequentially make your way through the data because in the memory, you only have 1 object at a time. If you want, this is pretty much the same thing as comparing downloading a whole movie from the internet, like the entire file of the movie, versus streaming it on Netflix. If you stream it on Netflix, you only ever have a few seconds or maybe 1 minute of the movie that is in your memory, and it just downloads what it needs to show you, right? Does it make sense? Yes? No? Yes? Awesome, you're following. So this is just like downloading versus streaming. Okay, and finally, because we have Spark, we can also decide to parallelize, which means that instead of doing everything on the same machine, we can put 2 on one machine, 3 on another machine, and then each machine is doing it in parallel, right? So this is yet another way of doing it. So of course, it can take a lot of machines, right? But this is always a compromise to make. All right, so now I'm about to wrap up. So RumbleDB can read data from S3, from HDFS. It even works from HTTP. So if you have a JSON file on the web somewhere, you can literally put HTTP blah, blah, blah as the actual path in JSON doc or in JSON file. It can also read from your local hard drive. It can read from Azure and so on and so on. What can it read? It can read JSON, it can read CSV, can read Avro, Parquet, Roots, that's for CERN, high energy physics, libsvm, that's for machine learning, and so on, all of that. As you can imagine, if you read JSON, most of the time it's going to create an RDD. If you read CSV, Avro, Parquet, and so on, it's going to create a data frame. So RumbleDB is able to create data frames internally if it detects that it's faster. Okay. And you can also use it from Java, even though we don't have many people that actually do that. So the most convenient way is really to have a Jupyter notebook and to read the data from the cloud and read all of these formats. So now I have one more slide. So this is to say that if you have small sequences, so the empty sequence or just one item or a small sequence, this is all local. It doesn't even use Spark. It's just local code that iterates. And all expressions can be implemented if it's very little data just on the local machine on your laptop. If it's very large, like you read a big file on S3, it's going to create an RDD, right? So this is going to create an RDD where each one of the objects here is just a Java object that is in your RDD. And of course, if you try to navigate on that, it's going to transform this dot country as a flat map transformation on the RDD. Why flat map? That's because if there is the property that doesn't exist, it has to skip it. If you have map, it would create an empty value instead. So that's why a flat map, right? And these dot countries is put in UDF is for user-defined function.
Can you repeat when RumbleDB uses an RDD directly instead of via a Spark data frame?
Yeah, let me explain. So in the case of Avro, Parquet, CSV, you have a schema. You see the name of the columns and you see what's inside. So it's able to infer a schema and to structure it in some way. So this is why in that case, if you have Parquet, you would directly create a data frame. But if you open a JSON lines data set, it might be a huge mess in that data set. Let's take the GitHub archive, for example. The GitHub archive data set doesn't fit in a data frame. You can try, you're going to have a nightmare doing that because there is heterogeneity and the types are changing and so on. So if you open a JSON file in general, it will create an RDD and not a data frame, right? But the nice thing is that from the user's perspective, it looks the same in JSONic. It doesn't make a difference. The only thing you will notice if it actually creates a data frame is that it's going to be faster. That's the one thing you'll see, right? Yeah. Does it answer your question? Awesome. Thanks. All right, make it pro. All right, so RDD-based execution, countries. Yes, so that's why what I said with the RDD. Do you see here? It's heterogeneous. Here we have arrays, we have strings, we have null, and so on. So this is why RDD allow you to have these heterogeneous sequences of items. If you had a data frame, the sequence would be homogeneous. It will always be integers or always strings and so on. All right, and now if you open the array, then everything that's not an array is just dropped, and the content of the arrays is then unboxed as a sequence. This is also done with a flat map in Spark internally. And then if you have distinct values, it's also able to map it to a distinct transformation in Spark. So you see there's a lot of things that it manages to push to Spark, to push down to Spark is the word for that. All right. Here's an example now where, so here it was JSON, right? So this is why an RDD. Now I have a Parquet file. So I have a Parquet file. Obviously, there is a schema in that file, so I can directly open it as a data frame like that. You see now it's highly structured because there is a type in every column. That's going to be much faster. because now what's going to happen is that if it's heterogeneous, it's going to be an RDD. If it's homogeneous, it's going to be a data frame. Internally, the execution will be different, but from outside, these are just sequences of items, always. So the data model is just the same. So this is all hidden. So you see, you can select, project, group, join, generic. All of that can either be done locally if it's small, or in parallel on Spark if it's big, and the switch is automatic. All right, here's another example with the streams of tuples. Now, how do we execute flower expressions? So imagine I have this data set. Then I iterate with a for clause that creates a data frame. So the flower expressions are executed with data frames, where each variable is a column in my data frame. $person in that case is bound in turn to all of that. Then there is another for that's creating another column in my data frame, where is going to do a selection in SQL. Then I have a let that adds a column and return, and then I map that back to an RDD in the general case, right? So this is advanced, right? This is really what's hidden from the user. RumbleDB does it in such a way that the user doesn't have to do that ever again. You don't even have to worry anymore about RDDs and data frames and so on. So the flower expressions can either be executed locally. So the first one would be local because that's small enough that it's just done locally on your laptop. The second one, it would detect that this is a very large JSON file on the cluster, and that one would be executed with Spark. But you see that the code is exactly looking the same, whether it's local or whether it's on Spark. It's just the same. And coming back to the expression, so that's something I already showed you, it can be executed, the first ones, very efficiently directly on your laptop. And if you start having JSON file, Parquet file, and so on, it automatically switches to Spark RDD, Spark data frames. In some cases, like the last one, it's even able to generate native Spark SQL queries, which is even faster.
What will RumbleDB use if it is not using Spark?
If it's not using Spark, it's just going to run in Java native. So it's literally just going to be Java code that executes on your machine or remotely on the cluster, right? That's the idea. So these are all ETH students who implemented that, yes? Native, yes. So if it were not native, what happens is that this $obj.foo plus 1, right here next to number 5 for those on Zoom, $obj.foo plus 1 would be compiled to and executed in Java and packed as what is called a user-defined function. This is not efficient because it requires shipping it to the cluster and so on and so on. So that's not efficient. Native Spark SQL is that you know that this is a data frame when you have this for let and so on. So since you have a data frame, this let $p blah, blah, blah can be directly written as a Spark SQL query on that hidden data frame. That's what it means. You don't even compile it to Java or anything. You directly write it as a Spark SQL query. And that's going to be much faster, massively faster. Does it make sense? Okay. Okay, so overall, everything, a lot of optimizations are determined statically before you even execute. It makes the choice of what to execute where. And then you just go annotate the whole tree saying, okay, this is local, this is on Spark, this is an RDD, this is a data frame. It all takes care of that as soon as it compiles your query. And that's yet another example of how it would elegantly hide all of these execution details for that specific query. Right. So I'm almost done, actually. I think there's really not much left. So this is to say that we are migrating slowly to what is called a lake house architecture, where we have data lakes, but slowly people are adding update facilities and indices in there. So that's a bit out of the scope of the lecture, but this is where things are going. That with the Delta Lake, for example, you support updates that can be done there. Then you have a full integrated system for machine learning. That's called the Lakehouse right there. We compared RumbleDB in a paper with, I encourage you to read the paper, by the way. It explains what I've been telling you. It's not significantly slower than any other system. So it makes it more convenient, but not slower. Right. What is this? Yes, so this is to show that you can use RumbleDB to clean up, validate, convert your data to data frame before you use machine learning. So you can actually, this is really advanced here, you can declare types, you can validate your data as certain types, and then RumbleDB will be able to use data frames, even if it was not a data frame on disk. Right, so this is a JSON schema, by the way. Right here, what you have in declare type is a JSON schema. All right. What was the cleanup proposal? Yes, that's a way, the sort of things you can do in order to clean up a bit your data. So this data set wasn't very clean. So there is a string, there is an array in here. And here, that was converted to a data frame using some JSON code and a schema. Right, so it's more convenient to use. And that's, you can look at it offline. This is the sort of things you can do in order to do the cleanup. All right, and finally, but that's the final appetizer, you can also do machine learning with RumbleDB. There's a whole machine learning library. You can actually, once you have prepared your data and validated it, to turn it into a data frame, you can use machine learning features in order to train and to make predictions on your data. But this is largely out of scope of the lecture. That's just in order to tell you that this exists. It actually uses, yes, I see the comment on Zoom, it actually does use SparkML. What's done behind the scenes here is that it automatically compiles everything to SparkML in the background. So this is indeed a very relevant comment. All right, this is it. That's it. So I'm actually done with the material. I recommend you read the paper on RumbleDB. I recommend you do the exercises, try out the sandbox, write as much as you can. On the exam, you will have to write JSONic queries. We will, of course, give you more details on the exam, but I encourage you to really do the exercises and learn JSONic. And who knows, maybe it's going to be useful in your own projects, student projects or master thesis, and so on. So thank you very much, everybody, for attending. Enjoy your meal. I'll see you next week, but next week will just be a wrap-up, right? We'll just, FAQ, wrapping up, maybe a quiz with everybody, but there will not be any new material. We are done. Congratulations. You've made it to the entire material of the lecture. So thank you very much. Enjoy your meal and see you next week.